So our next speaker is Vlad Kobzar from NYU Center of Data Science. He will talk about potential-based bounds for geometric stopping version of prediction with expert advice.
Great, thank you. Our paper is new potential-based bounds for the geometric stopping version of prediction with expert advice. I will give some background on this prediction with expert advice problem, and then I will summarize our contribution, including an upper bounds framework and a lower bounds framework. Prediction with expert advice is a classic problem in online machine learning. It's a repeated two-person zero-sum game. We will focus on the geometric stopping version, where the stopping time is sampled from a geometric distribution G with mean 1 over epsilon. 1 over delta. At each round, the predictor player uses guidance from a collection of n experts with the goal of minimizing the difference, a regret, between the player's loss and that of the best performing expert in hindsight. The expert losses are determined by adversary, so this is a completely distribution-free adversarial model. While player strategies leading to upper bounds are known and often based on potentials, for example, exponential weights, there's no previously known lower bounds for geometric stopping for general n number of experts. Our contribution, let me frame our contribution in the context of previous work. We developed a viewpoint based on partial differential equations on player and adversary potentials used for the fixed horizon version of this problem, where the stopping time capital T is fixed. This paper extends this PDE-based viewpoint to the geometric stopping version. Specifically, if an adversary strategy for the fixed horizon problem does not depend on time, if it is stationary, then it can be used for the geometric stopping problem. Technically, given a fixed horizon potential, its Laplace's transform gives a geometric stopping potential. The intuition is that this transform is the expectation with respect to the exponential distribution, which is a continuous limit of the geometric distribution. And our key practical result is that we obtain the first lower bound for general n for the geometric stopping problem. Let me now formally define this problem of prediction as expert advice. In each period T, the player determines the mix of n experts to follow by selecting a probability distribution over n outcomes. The adversary allocates losses to the experts by selecting a distribution AT over an n-dimensional hypercube. The expert losses QT are sampled from AT, and the player's choice of the expert IT is sampled from PT. Both samples are revealed to both parties. The instantaneous regret R tau, it tracks the difference between the expert loss QI tau and the loss of each expert. Just as a reminder, Q tau is the vector of losses of each expert, and QI tau, the entry, just the expert that was selected by the player. So this tracks the difference. The accumulated regret XT is just the sum of R taus for all previous periods. The final regret for the fixed horizon version is the largest entry of X at final time in expectation over player and adversary randomization. And then in the geometric stopping time, you also take expectation with respect to the geometric stopping condition. Let me pause for a second in case there are any questions. Okay, now let me describe our viewpoint on this problem. Our viewpoint on potential uses the value function of the game. So here we focus first on player strategies and upper bounds. We assume that player is Markovian, that is, it depends only on the cumulative regret X. The value function of that player VP is the expected final time regret achieved by this player if the game starts with realized regret X, and it assumes that the adversary behaves optimally. it is characterized by the following equation. Vp at present x is equal to the probability of stopping delta times the value realized at the stopping, which is the max function, plus the probability of continuing times the value function at the next step, assuming that the player behaves in accordance with the chosen strategy and the adversary behaves optimally. Our upper bound potential is a function W hat from Rn to R, which is non-decreasing in each I, which solves the following PD. So we will go through the PD in more detail, but let me just first mention that the first line of this PD is there to ensure that as the game evolves, the potential does not increase. The second line there is simply to ensure that the potential is linear in the direction of vector of all ones. This is reasonable because the final value function, the max function, is also linear in the direction of vector all ones. And then the associated player is simply the gradient of the potential. This construction leads to an upper bound on the value function associated with this player if the difference between W hat and the max function is uniformly bounded below. We will later sketch the proof of this result of this upper bound, assuming that it's bounded below by 0 for simplicity. Let me just note that this bounds, the upper bound on the value function bounds the regret above because the value function evaluated at the initial point when the accumulated regret is 0 is simply the final time regret if the player behaves in accordance with the chosen strategy and the adversary behaves optimally. Let me briefly mention how we construct a geometric stopping potential from a fixed horizon one. It is illustrated by the exponential weights, which is a widely known example in online learning. The fixed horizon potential WE is just phi of x, which is a well-known soft max function with a parameter eta, plus some constant that depends on time, the number of time periods. So it is associated with the exponential weights player, which is the gradient of this potential. And then the standard fixed horizon upper bound is known in the literature, just the potential evaluated at 0 plus 1/2 eta, the parameter, times the number of fixed steps. So fixing this constant k equal to 1/2 eta ensures that the regret is bounded by the potential evaluated at the initial point when the cumulative regret is 0 and capital T is the number of remaining time steps. The Laplace transform of this potential, which is very simple and can be, can be evaluated explicitly, gives us the geometric stopping potential. It is very easy to see that the transformed potential W hat E for the exponential weights satisfies the PD that I wrote on the earlier page. This is just the exponential calculation where we know that the soft max function bounds the max function above. There is a standard bound, so d square phi is the Hessian of phi. There's a standard upper bound, which is very simple. This is just upper bounded by the parameter eta, and taking kappa equal to this specific value ensures that the first inequality in the PD is satisfied. Also, since this potential phi is linear in the direction of vector of all ones, this means that W hat satisfies the same property. Also, since phi is convex, this quadratic form is bounded below by 0. Therefore, the difference between the potential and the max function is also uniformly bounded below by 0. So let me now briefly sketch the proof of the upper bound. So the issue is that we want to use induction backwards from the stopping time, from the final time, which is a verification argument from optimal control theory, but we don't know the final time. So our solution is that we introduce the same, a new problem, which is the same as the original problem, except that it ends at time t0 if it doesn't end early in accordance with the geometric stopping condition. By a simple argument, we could show that the difference in regret of the new problem relative to the original problem goes to 0 as t0, as the time t0 goes to infinity. Therefore, it suffices to bound the value function g of the new problem, and it is given by a dynamic program where at final time t0, this is just the max function, and in all previous times, the formulation is the same as for the as the characterization of the value function VP. So this line here is the same. And then the proof of the upper bound has two steps. In the first step, we control the increase in W as the game evolves. As a reminder, the instantaneous regret is simply the loss of the expert chosen by the player minus the loss of each expert. By the linearity in the direction of vector O1s and using Taylor's theorem expansion, we can bound the difference between the potential at present and the potential at the next step in expectation. And this very simple computation shows that this potential is bounded by the largest second derivative of the potential. And then from the PD definition of the potential, we get this bound. The reason the first derivative is eliminated is because of the choice of P. This term eliminates the first order term of the Taylor expansion of W hat. And then rearranging the following, we get this inequality. And then in the second step of the verification argument, we just show that W hat bounds the value function of the new problem G, and therefore W hat bounds the actual value function that we're interested in by the convergence of G and V hat. The initialization is simple. It's by the initial conditions. And then in the inductive hypothesis, we assume that the inequality is satisfied in the future, in the next step. And we here show that therefore the inequality is satisfied at the present step, at the present time step. So the first inequality simply follows by step 1, where we could add the expression in brackets. The last inequality, so we cancel therefore W hats. The last inequality follows by the inductive hypothesis, where we replace W hat by G. And then the last equality follows by the dynamic programming definition of G. Evaluating the specific potential for the exponential weights, which I defined before, gives us the following lower bound on regret, which is the square root. And this improves on the best previously known lower bound, which was in Gravin et al. 2017 paper. Our main contribution, however, is lower bounds, and the framework that I described before
you have
also
1
works
minute.
for.
Sorry to interrupt. You have 1 minute left.
1 minute. So our framework also works for lower bounds. So I will wrap up very quickly. We assume also that the adversary Markovian and balanced, and by balanced it means that the losses have the same expectation. The value function for this adversary has a similar definition for the value function before. We also have a same PD-based definition of a lower base potential, the inequality here than in the other direction. And by a very similar proof, we show a lower bound modular discretization error E. And this lower bounds lead on the regret bounds. And in estimating the expected value of the change of the potential, the dependence on the player strategies in the first order term, which also gets eliminated because A is balanced. And so the dependence on A is just on the adversary remains on the second order term, and then you analyze the second order term. And then we use a very simple heat-based adversary to obtain the upper bound, where the lower bound, where our potential U hat is just a Laplace transform of the solution to the linear heat equation. It satisfies our definition of the lower bound, and it has the same leading order asymptotics as the exponential weight upper bound. It is also leading order optimal, and we also give a non-asymptotic guarantee where the discretization error is computed explicitly and is similar to the consistency schemes in the consistency error in the finite difference schemes for differential equations. So this is the conclusion. Thank you very much. And I will be, if there's any time, I will be glad to take questions.
The next question is for Vlad. Vlad, are you still there?
Yes.
So the question is whether your new technique can be applied beyond the setting of the mixed experts and non-experts.
Well, certainly the key aspect of our framework is the dynamic programming definition and the of the value function and the PD, essentially PD limit of the leading order of the value function. So to the extent you can formulate your online learning problems in this dynamic programming fashion and obtain some kind of a PD limit, the framework should work. We're working on various generalization of it. We don't have any concrete results to report yet, but we think that the framework should be quite general. As you know, we started with prediction as expert advice with fixed horizon, which was really the classic setting. Then there were some recent papers on the geometric horizon where the stopping time is random. So that was one of the most natural extensions of the paper. And there's really nothing specific in this framework to the experts. And so the hope is that, yes, that it can be used broadly to study online learning problems, but especially the lower bounds for the online learning problems. Let me just emphasize that previously potential-based methods were used to study, to give upper bounds, and lower bounds were obtained by random strategies and more probabilistic random walk methods, which usually came from some central limit theorem, and the discretization or non-asymptotic result was not clear. We extend the potential-based framework to lower bounds. So the hope is that, in other settings where it is difficult to obtain lower bounds or to study kind of a random process associated with lower bounds, that the PD framework could simplify that methodology.